This is the Smart Buildings Academy podcast with Phil Zito, episode 232. Hey folks, Phil Zito here, and in episode 232 of the Smart Buildings Academy podcast, we are going to be talking about how to design inputs and outputs for your controls hardware designs. So if you recall in our previous episode, episode 231, we started to unpack the 5-step controls engineering process. And in this episode, we are going to be unpacking the input and output process. So in front of me on my screen, which you cannot see because this is an audio podcast, I have a set of MEP plans from the Baltimore City Public Schools that I found on the Google search in the public domain. So I'm going to be talking through this and kind of explaining my thoughts on how to approach actually creating the inputs and outputs. And this ties in pretty well to a couple things. One was some questions I had in our live office hours this morning, and some questions I've just had across Facebook and LinkedIn recently. So what I want to do before I unpack that real quick is to remind you that everything's going to be available at podcast.smartbuildingsacademy.com/232. Once again, that is podcast.smartbuildingsacademy.com/232. And if you are listening to this episode on the date it was released, then you still have today to go and take advantage of our early access program for Controls Engineering Bootcamp. This course will teach you how to create hardware designs for your control systems, teach you the inputs, the outputs, how to create network architectures, how to select controls hardware, how to size valves and dampers, and everything in between. So if you're looking to do hardware engineering on control systems, I encourage you to join as part of our Controls Engineering Bootcamp early access program. You'll be able to save 75% off the cost of the course, as well as being able to give feedback as we create the course. Every course goes through the early access program as part of our course creation process, and that enables you to give feedback as you move through the course. All right, so right here in this system, I'm looking at a middle school, and I'm going to first start to unpack a fairly complex system, and then I'm going to go through a less complex system. Now, the reason I'm going to start with a complex system is because I want to kind of talk you through all the different parts and pieces I would commonly look at, what my thought process and methodology is in approaching them. Now, I want you to realize that in a traditional engineering approach, what I would actually do is start with the smallest system. I would typically start with terminal units and exhaust fans, and then from there, I would move towards my larger airside systems, and then I would move to my hydronic systems. And the reason I take that approach is because if you recall in last week's episode, or actually it's 2 weeks ago now because I didn't do a episode on the week of Christmas, but if you recall in episode 231, we talked about doing the I/O first, then the hardware, and then the architecture. And the reason why is if you approach the architecture first and then the hardware and then the I/O, the problem with doing that is you may oversize hardware, you may undersize hardware, you may employ architectures that really aren't the most cost effective or don't achieve the outcomes that you're trying to achieve as part of your project. So what I want us to focus in on here is starting with the I/O. And when we start with I/O, we are going to bounce between two documents. We're going to start on the MEP set, which is what I'm looking at on my screen, which once again, I realize you can't see. So if you are looking to see this, then I'd encourage you to join tonight's live stream on YouTube at 8 p.m. Central Daylight Time, which will be about essentially creating this architecture, or rather I/O selection approach that we're taking right now. Now, like I mentioned, I like to look at the I/O and I like to move through it, and I bounce between the MEP set and the specification. Specifically in the specification, I like to look at the section 2, which is the material or parts category. And what that enables me to see is specific parts and pieces. And that'll become really important as we move through our I/O selection. And it should actually help us reduce the time and effort in our I/O selection. So right here on my screen, I'm looking at an outside air system. And this is a slightly unique system in that it has a building warm-up bypass that actually ends up dumping the exhaust stream back into the outside airstream. and has two motorized dampers, one on that bypass loop and one on the incoming outside airstream. Now, I like to approach whenever I engineer a system, I like to either start from the left or the right, never from the middle. And the reason why is that way I make sure I get everything that I'm supposed to be touching and selecting as part of my system. So, what I'll typically do is I will go and I will read through the sequence of operations so I kind of get an idea of what the system is capable of doing, how it is functioning, and kind of what everything is going to be doing and working with. Now, in this specific drawing, there's actually a unitary controller, or rather, an embedded controller for this system. And that's one of the things I'll bring up a little bit later in the episode is being careful on whether the system is embedded or whether it is a building automation system, rather a DDC controller that you're providing and you're providing the IO. Because I'm seeing increasingly that we're seeing smart equipment or embedded controls in equipment, and we are just doing interfacing. I'm seeing that becoming increasingly common just due to the reduction in cost, both from a labor perspective as well as the potential cost from a materials perspective. So granted, while this drawing, if you were to go look this up, is a embedded controller, I'm going to treat it like it's not an embedded controller. Otherwise, this would be very boring for me to just say to you, well, find the BACnet interface and call it a day, because that would get old pretty quick. So as I look at this unit, there's a couple nuances I notice about it. It's got that warming bypass. It's a 100% outdoor air unit, but it's really not because it's got that bypass. So it has two opposed motorized actuators. It actually has a motorized actuator on the exhaust as well. Additionally, it has some interlocks to these motorized actuators as well as to some of the drives themselves, which is kind of interesting. And it also has a face and bypass damper. That's why it's really important that you understand control system theory as you approach engineering. You know, selecting the IO honestly is not that difficult. Once you learn the terminology and you learn the basic things to check for on your IO when you're selecting them, it becomes pretty much a matter of routine. You just go and say, oh, I need a temp sensor. Is it a probe or is it an averaging? What's the size of the duct? So I know the right size of the probe. What kind of element does it need to be? What kind of signal does it need to be? And most of this will be guided by the specification. So it becomes actually rather easy, relatively speaking, for you to do this. So I'm going to start from the left and I'm going to move to the right. So when starting at the left, I see that I have a differential pressure sensor that is going to my building air terminals. It says refer to plans for location. That's important to note because oftentimes on the actual mechanical plans, you will go and have the placement of your DP. Now, why would that be important to note? Why would where the sensor is being placed be important for us to understand? Well, for two reasons, actually. One is if we take the approach, which is normally my approach, which is that everything within a control sequence for a specific program should ideally be in a single controller. That way, you're not reliant on network transfers. For example, we could wire up that DP to the closest air terminal. And a lot of folks will do that. And the problem with doing that, in my opinion, in my experience, is that if we have to transfer that signal across the network and we lose a network for whatever reason, we have just effectively lost the primary process variable for that system. I mean, differential pressure on airside systems is one of the primary process variables for process loops. And it's going to drive the speed of that VFD drive. And essentially, without that, we're going to be really kind of struggling. I don't see how we control it, to be quite frank. I was trying to sit there in my head while I was talking, and I'm like, how would we control this? And I'm like, no, we really are not. I mean, we could put a false DP in there, but then you just could be tripping high statics and low statics as soon as boxes start to change. So we need to be cognizant of how do we wire things up. So understanding that referring to the plans for location is going to be pretty important because that's going to tell us, is it far away or is it close? If it's far away, we may want a 4 to 20 milliamp sensor. And if we go into the actual drawing or the specification that calls for a 0 to 10, but we realize it's 300 feet away, we may go and do an RFI, or rather an RFC, and say, hey, this distance is pretty far. Let's get some clarification on, can we use an alternate of a 4 to 20 in lieu of a 0 to 10 so that that current can handle that distance and voltage drop a little bit better? That would be important for us. So moving right along, we see a discharge air temp sensor, we see a smoke detector safety, we see a high limit safety, we see a bunch of things. Now, when I try to look at these, I first look through the system left to right. So I see all my IO here, I see all my control devices here. But then once I've seen all of this, I print it out on 24 by 36 and I get a highlighter. And then the first thing I like to do is my sized outputs. What do I mean by sized outputs? Valves, valve assemblies, valve actuators, damper actuators, damper assemblies. I like to understand those because I have to do calculations. I have to understand foot-pounds for my torque. I have to understand my CV ratings for my valves. I have to understand my sizing. What are my valve transitions for my sizing? What am I stepping down or stepping up to as far as pipe size? I need to understand all of these things, and these are calculations. Whereas most of the things in here, my smoke detectors, my airflow switches, my static pressures, I mean, I can quote off the top of my head what those part numbers are going to be because I've used them so much, right? Like the Cleveland Air 460s or maybe a 465s, right? Just depending on whether we want push button reset or non-push button reset. But we can go and real quickly figure out what are we looking for. Hawkeyes maybe for current sensors, etc. But with actuators and valves, those, especially when you have multi-air handler sites. So this site only has 2 outside air units, and then it has a bunch of terminal units and a VRV system, or a VRF system rather. A lot of places that are going to have tons of rooftops, tons of air handlers, tons of terminal units. And when you have those kind of systems, making a mistake in the actuator sizing, making a mistake in the damper sizing, making a mistake in the valve sizing, that can get really costly because you can't just go and make them fit. I mean, you could kind of, sort of, but it'd be really a hack job and it really would degrade the performance of the system if you can even get it to fit. But, if I accidentally get a probe wrong, that's not that costly. Yeah, I can hear you that, yeah, across 100 units, it might get costly, but it's not going to be quite the same as my dampers and actuators because I can usually go transfer those probes to another job and then go and get the right probes. It's a little harder to do when you've got an assembled damper and an assembled actuator. Those are a little harder to fit into other projects. That being said, I like to do my sized systems first, and then I add them to my Excel sheet like I discussed in last week's episode, right? We go and we have an Excel sheet where we start to build out our points list. From there, I go to my inputs, and this is where I work left to right. So I've got 3 types of inputs, right? I've got voltage and amperage inputs. I like to kind of put those in their own category because they usually require some form of external power supply. Then I've got my resistive inputs, and then I've got my switch and safety inputs. So as I start to list these things out, I start to go through them. I find my DP, most likely going to just use a standard Varus DP sensor, probably a 4 to 20 or a 0 to 5. And then from there, I move to my temp sensor, which is discharge air. So it's most likely duct probe. Discharge and return air are usually probes, and middle, so mixed air and preheat are usually averaging. And what's the reason behind that? So when we're talking about return and we're talking about discharge, usually that is, I don't want to say it's not stratified, but it's usually less. It's usually less turbulent, and it's just air that we can get a sample of and not have to worry so much about having potential cold spots that are going to freeze coils, which is really one of the main reasons we use an averaging sensor, because especially in the mixed air compartment or in the preheat compartment, using an averaging sensor is going to give us a sensing of if there are any potential pockets of cold air that could potentially damage our coils or trip our low temp alarm sensors. So by having an averaging sensor, we are then better able to go and actually prevent those issues from happening and just have better control. Whereas with return and discharge and outside air, we're tending to get a more stable sample. I don't want to say it's always that way because there are plenty of very compressed units that have the discharge air literally right after the fan assembly, and obviously the air is very turbulent as it leaves the fan. So we have smoke detector that's typically provided by others. Our differential static pressure, high, limit, and airflow switch. Those are going to be your standard Cleveland. Cleveland controls? Why is it blanking me? I feel like I said it earlier in this podcast already. The AFS 460 and 465, which I think the 460 is the push button reset and the 465 is the automatic reset. I like to use push button resets for everything because it forces people to go up to the units. Granted, they can always put duct tape over the reset. Come on, you've probably seen that too. And just make a manual reset and automatic reset. Then we get to the VFD and we need to make a decision. Are we using the internal command and safeties of the VFD itself, or are we command and status of the VFDs itself, or are we going to add our own wiring, or are we going to use a BACnet interface? And this is where looking at both the specification and the MEP set will really help us out. And then we can always submit RFIs or RFCs if we're not clear on something. We see we have a current sensing. I'm assuming since it says CS that is a current switch, and I'm assuming C is command, and VFD is obviously VFD. Granted, I could go to the legend and look all this up, but right now we're just going to go with it. Okay, so I see that I've got a command status. Usually that's going to be like some sort of Varus sensor. That is going to be put on one of the legs, and that's going to help us determine if we've got, like a loose belt or something. Command's usually going to be like a rib U1C. That's going to be basically we're going to energize a coil from our controller and allow the voltage to pass through one of the sets of contacts, usually the normally open set. And then VFD speed, that's usually going to be an AO. We've got a couple more temp sensors. We've got a low limit. We've got our face and bypass coil, although this face and bypass coil does not have any valves on it, which is interesting in and of itself. I would be very interested to look deeper into the hydronic system if I had time, but I'm not going to do that and make you all wait while I dig into this further. We've got our traditional face and bypass, normally closed, normally open. So normally open to the coil, normally closed to the bypass. And we see we've got an energy recovery wheel. We've got our basic start-stop command on it. And then we've got a DP switch across our filter, a temperature and humidity. And we see that we've got some actuators and dampers on our outside air section. And then on our exhaust section, moving from left to right, we've got a low limit for our static pressure, smoke detector, airflow switch, temp and humidity on the exhaust return, which is very interesting. They're most likely doing some enthalpy comparison to decide whether they're going to run the energy recovery wheel or not. We've got our switch across our filter, and we've got a temp sensor, and then we've got a fan after the energy recovery wheel and a damper that is interlocked with that fan, which, I mean, makes sense. You don't want to go in, close the damper and turn on the fan. That would be bad. So as we list all these things out, I'm increasingly noticing that on a lot of MEP sets, people are including points. They're including points lists. I feel that that's because a lot of mechanical contractors nowadays are starting to have their own controls groups. They're starting to realize that by really dictating this out, they're not only providing a better service to their customer, but they're also increasing the likelihood that things are going to be successful. Now, I do notice some what I believe to be typos in here, but I'm not 100% sure. As I look at the bypass dampers, as I look at intake dampers, I'm starting to notice that they are all AOs, which is really weird because they have alarm type Boolean command failure. They have damper command, but yet they're analog outputs. So wouldn't that be binary output, being that these are on-off positions? And I go and I validate that against the sequence, which indeed does say that these are going to be on-off, or rather open-closed. And so I think that's a typo. That's something I would probably RFI. Now, that being said, I also noticed that the face and bypass damper is indeed AAO. It is going to shift, and that's normal, right? You're going to blend your bypassed air and your face air based on what you're trying to drive the temperature to be. So we can see that all of that's going on. And that's it for that unit. I mean, pretty straightforward. I would build out my list, and now I would be able to start sizing my hardware. Now, we're not done yet. We're going to talk more, so don't hop away. But I am going to tell you that in next week's episode, we are going to start to explore how do we do hardware sizing for our actual controllers. We're also going to look at application-specific controllers. We're going to look at advanced application controllers. We're going to look at building controllers. We're going to talk about when to use IP controls architectures versus when to use just regular MSTP control architectures, and a lot more. So this is going to piggyback into that. But with that, I want to move on to this water sourced heat pump. So I see this in a lot of schools, water source heat pumps or VRFs. And it's very interesting because if you didn't know better, if you were an inexperienced engineer and you didn't know better, you could actually get caught off guard by this, because it's only at the very, very bottom that it says the building automation system shall have factory mounted controls, or the unit shall be provided with factory mounted controls and all factory accessories required for BACnet integration. The unit shall operate under their own controls. But if I scroll up and it says building automation system interface, building automation system shall send the factory installed controller occupied heat and control modes. Now, in my experience, I would take that as, oh, okay, I'm going to go and have this unit, right, this variable speed water source heat pump, I'm going to have a BACnet interface to that. But then I go up to the next unit and it says the building automation system shall send the field installed controller, occupied bypass, morning warm-up, pre-cool, If BAS is not present or communication is lost with the BAS controller, the unit shall go to these default modes and set points. So I'm a little confused now. Is this single stage and two stage water source heat pumps? Are these systems that are going to be having building automation controllers on them? Or are they going to be having BACnet interfaces? Which one is it going to be? What am I going to be doing with these systems? And therein lies one of the things that can kind of get you hosed up, especially when you're dealing with schools or maybe potentially low cost projects that have factory packaged controls, or maybe they have the option for factory packaged controls, and we're just doing an interface. So we really got to get clear. I would submit an RFI to make sure that I really understood, is this really a field installed controller, or is this a factory installed controller that's being installed in the field, but yet it's not really a BAS controller? Do you understand what I'm saying there? I really hope you do, because that's an important concept to get across. Because if you don't understand that, if that's not clear, then you can make the mistake where you buy a controller, you buy all these IO, and you provide them on the job site, you show up, your techs show up, your installers show up, and it's already got controls. And you're like, crap, I spent all this money. So it's important to not make that mistake. Now, from a controls perspective, I mean, this is very simple. It's got some temps on the heat pump return and supply. It's obviously got its heat pump with a flow interlock. It's got a space thermostat, command and status for the supply fan, and a temperature on the supply air to the spaces. So a pretty basic architecture approach for a pretty basic system. So something that is not going to be terribly complex and isn't going to really challenge us. Now, that being said, what I want you to pick up from this is that a lot of these systems are not going to be that complex. Whenever I go onto Facebook, whenever I go onto LinkedIn, and I have conversations with people about what do people need to know in order to do hardware engineering, in order to do installation, in order to do programming, oftentimes I will run into people who will say, well, you need to have this level of experience because you could potentially run into this type of system that's super complex, heat pump chiller or something like a two pipe system. And it's a complex system and it takes a lot to control. But the reality is that your likelihood of actually running into that kind of system out on the job site is slim compared to air handlers and VAV boxes. So what I really want you to focus in on when you're doing an IO selection is start to learn the common pieces that you will find in your systems. Start to think of your systems as, is this a piece I need to be providing? How should I provide it? What should I be focused on? And start to build out your systems accordingly. Start left to right, really read the spec, read the sequence, read the MEP set, submit your clarifications as early as possible, and then pick your parts. Start with your engineered parts first: flow stations, dampers, actuators, valves, valve assemblies, all these things that need to be sized and engineered. Take care of them first. They're also usually the most costly parts of the job. And then from there, and only when you've done that, should you move on to looking at your other parts of your system. Then you start to look at your basic sensors. You look at your basic outputs. You look at your different safeties and you work through those. If you follow this process, my friends, you will find that engineering systems is a relatively repeatable process, and you will start to build out a list of IO, a list of sensors, a list of devices that you can use as templates, as I discussed in the previous podcast episode. And when you build out those templates, then creating a hardware engineering design becomes quite quick and quite easy. That's why I would always argue that you should be able to do submittals pretty fast, because you should be pulling from a template library. A lot of folks would feel like you have to do it fresh from scratch each time. That's a really inefficient way to do things. And you will never hear me, I don't want to say never, but you will almost never hear me suggest doing something from scratch. I will almost always say use templates, use patterns, repeat, 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 because that's how you get efficient, and efficiency saves money and makes you profitable, which gets you raises and keeps your business afloat. All right, if you have any questions, please go to the comments section or the discussion section, depending on where you're listening to this. I encourage you to reach out. And if you are at all interested in hardware and engineering design, then definitely check out our Controls Engineering Bootcamp. It's going to be an awesome experience for everyone who joins. Right now, I think there's 34 spots available still. So be sure to enroll in that at podcast.smartbuildingsacademy.com/232. All right, folks, thanks a ton, and I will talk to you next year. All right, take care.